Let's see what we achieved until now. To resolve the problems of type static range query, we can use a naive approach, which take linear time for a single query. We can use also a dynamic approach that compute all the answers for all the ranges. It's constant time for a single query, but as you see, quadratic time for the preprocess. We have to build a 2D array and put in the array or store on the array all the answers of all the ranges. And the square root decomposition, it's square root of n for time complexity for a single query, and linear time for the preprocessing, and square root of n to build the array of blocks square root decomposition. And you can use also the sparse table. It's constant time for single query. For the preprocessing to build the sparse table is n log n, of course, and the size of the sparse table is n times log n, as you see. As you know, guys, as we have said in the previous videos, we can use the sparse table only on the function like min, max, mean static min, minimum range queries, static max range queries, static JCD range queries. We cannot use the sum, static sum range queries. Sparse table will not work here because, as we have seen, the function must be idempotent, which means f x return x, or the sum of x and x is not x, as you see. Okay. Because we continue to see how to improve this algorithm or this technique, let me show you how come this n log n. Why not in the previous video? Because in the previous video we did not use a lot of maths, but in this video, guys, we're going to use a lot of maths to prove some stuff. Okay. As we know, in 2D array is processed using these two nested loops. For example, if the size of the 2D array is, let's say, it contains A rows and B columns, so it will be processed like this. For E from 0 to A, or from 1 to A, from 1 to A, from 0 to A minus 1, and J from 0 to B minus 1, or 1 to B. With the same result, it will give me the same result, the two prototypes. The number of operation is how to compute the number of operation if the number of operation is K. Let's assume that we have K number of operations. So it's the sum from 0 to A minus 1 for this loop, and the sum from J from 0 to B minus 1 for this loop, K operation. For the first one here, we have here from 0 to B minus 1, which means we have B minus 1 minus 0 plus 1 operation. So we have B operation. Same, so we can say before that, we can say that we have BK operation for the first loop, for the second loop, for the nested loop here. Okay. For the second one, we have, for the first one, sorry, we have this expression, which means we have from 0 to A minus 1 operation. So we can compute the number of operations, the for the sum. A minus 1 minus 0 plus 1. We have A operation, which means we have A, B, K. So we can use these two nested loops. Give me this number of operations, which K times A times B. We know that the side of the sparse table is n times the floor of log base 2n plus 1. We can say that we can use these two nested loops from A is equal to log 2n because we don't reach plus 1 here, and the B is equal to n minus 1 because we don't reach n. If we use this formula from the previous slide, we can say that our fn is the function of the number of operations for these two nested loops is k times n times log base 2n minus k times log base 2n. Now to compute the time complexity of the pre-processing, we know that we have to find the asymptotic upper bound of fn. What's this? What this mean? The asymptotic upper bound. I speak in general here now. We have our function fn. Let's make another color for fn. Take this. For example, this is our okay. Let's keep it n here. We have here we have n and here we have t time. The time n represent the time function of the number of the size, the execution time, and we have to find the asymptotic upper bound, which is, for example, let's take it here and here. Okay. Asymptotic upper bound is a function is c times jn. What is c? What is jn? We're going to see this later. But here, as you see, from a integer n, let's call it n0 here. As you see, c times jn is greater than fn, or fn is less or equal than c times jn from this point. This is, we call this the asymptotic upper bound over fn. So we have to find the asymptotic upper bound of fn. Gn is the time complexity. We call this the time Gn is the function that represents the big O. Inside the big O, we can say we have to find Jn such that Fn is big O over Jn. So we have to find this. We can say that Fn is big O over Jn if and only if it exists a natural number n0 and a real number c. This couple of numbers for all natural number n is greater or equal of n0 and c is a real number such that Fn is less or equal than c times jn. This is easy to compute for this function. Now for this Fn, we take the first part here, and of course we know that the first part k times n log base 2n is always or equal than 2 k times n log base 2 of n for all n greater or equal to 1. It's obvious here, as you see. This makes sense. Okay. For the second part now, for the function, this one. Also, k times log base 2n is less or equal k times n times log base 2n for n for all n greater or equal to 1. This makes sense too, because we don't have n here. No. Okay. If we subtract these two, if we subtract these two parts, this one and this one, we're going to have our function here. So this leads us to our function fn is less or equal than k n log base 2n. Okay, this is our c times jn. You see here, for n is equal, for n0 is equal from n0 is equal to 1 and c is equal to k, we can say that fn is always less or equal than k times jn. Jn is our function, this function, this expression here. So we can say that fn is big O of n log 2n. This is the proof that the sparse table, the preprocessing of the sparse table costs n log n time complexity. Okay. As we see on the graph here, this is our fn in orange, fn here, and this is our c times jn in yellow here, yellow. Okay. So jn is, as you see on the graph, always from 1, always the c times jn is greater than fn. This is the harmonic upper bound of fn. Our goal now is to improve this time, this is a pre-processing time. To make it big O n, you have to move the log n factor from the pre-process. The main idea here is to divide the original array into an array of B blocks, array B blocks, of size BS. As like the square root decomposition, but it's not the square root here. The idea is to divide the original array A into blocks of the same size. That's called the size BS for now, block size. And build our array B, of course, of this from these blocks, which means we have to compute F of all these cells. F could be the minimum, max, JCD. Don't forget this technique, also because we're going to use the sparse table later, works only for the idempotent functions. So we have to compute F of this first B cells block, and the second, and so on until the last one. The tricky part here is to build the sparse table not on the original array A, but on the array B of blocks. So the size of the array B here is n over bs, because we divide the original array onto bs blocks, bs parts, if you want. So its size, the sparse table here on B, it will be n over bs times log 2 of n log base 2 of n over bs plus 1. So we have to find this bs. to find this BS, you can tell me we have our JN from the last video or the last slide, and just make Jn is equal to n. And so we have to divide log base 2 and log 2 of n over log 2n. This is completely wrong, guys, because this is not our goal. Our goal is to find a function fn that Jn is equal to n. You have to find this. Don't forget that the size of the sparse table on the array of blocks is n over bs times log base 2 n over bs plus 1. So we have to compute the number of operations, our function fn, on this array, for this preprocessed array. If we take here a is n over bs and b is log 2n over bs plus 1, and we use this function here, or this expression, what we're going to have here. So a is equal to n over bs minus 1, and b is equal to log base 2 of n over bs, and multiply k, the number of operation k, times a times b. This lead us and we develop for this product here, and we're going to have a function fn and compute jn, etc. But here we get, guys, I'm going to assume that this minus 1 not exist. This will lead us to the same result, for the simple reason to simplify the calculation. So our fn will be equal to k times n over bs times log base 2 n over bs. For this part, for this expression, we can use the logarithm properties that say that log a over b is equal to log a minus log b. Okay, so k times n over bs times log base 2n minus log base 2bs. We can just lead us to this expression, kn log 2n over bs and minus k times n times log base 2bs over bs. The question now, what will be bs to remove the log base 2n? For the first part here, it's simple to deduce that bs must be log base 2 of n. So our function fn will be like this. We replace bs by log base 2 of n. This is our fn. We have to find the asymptotic, our upper bound, the asymptotic upper bound for fn. Same here. We're going to compute or try to find Jn such as Fn is less or equal to C times Jn. As we have said in the previous slide, we have to find an integer n, 0, from that, above that integer n. For all integer n above the n 0, Fn is less or equal to C times Jn. For the first part here, it's very simple to deduce before the minus. We can say that k times n is less or equal to 2 times n for all n greater or equal than 0. Now, can we say for the second part of the function after the minus? Can we say that k times n log base to n log over log 2 base to n over log base to n is less or equal to kn? Let's see here in the graph. This is our kn and this is our function f. So this will lead us to this kn minus this is our function fn, and this is our c times jn. C is equal to k and jn is equal to n. Okay? As you see in the graph here, from 2 here, our function kn is greater than fn. So we can say that kn is the arithmetic upper bound of fn for all n greater or equal than 2. If we can say that, we can say that jn is equal to n, so fn is big O of n. We have proved here that the time complexity of the preprocessing on this sparse table. Let's come back to the first slide here. On this sparse table on the array B, we're going to build this sparse table on the array B, is the preprocessing is linear. So if we put all together now, we were going to divide the original array into blocks of size bs, which bs is equal to the floor of log base to n, and later we're going to see how we use the floor here, or why to use the floor, and build an array of blocks of size n over bs, and build the sparse table of the size on the array of blocks, which is for this size of the sparse table. The preprocessing here for all the stuff here, it will be we're going to build the array of blocks of linear time, because we have to read all the elements of the original array in linear time. And as we have proved, building the sparse table in the array of blocks, it will be big O of n. Once the sparse table is built, the sparse table of the array B is built, let's see how to query. Let's suppose that we want to know the range minimum query from left to right on the original array A. We can divide this range into parts, as you see, from L to L1 minus 1, from R1 to R, and from L1 to R1 minus 1. And you can say that the range minimum query in the array A from left to right is equal to the range minimum query on the original array A from L to L1 minus 1, union the range minimum query on the array of blocks B from L1 over Bs to R1 minus 1 over Bs, union the range minimum query on the original array A from R1 to R. You ask now, what's this L1 and R1? As you see here in the picture, we have to use the original the array of blocks B for this part, or this green part here, because it is computed, it's pre-calculated in the array of blocks. How to know the start point and the end point of these blocks? We know at the first time the left boundary here and the right boundary of the range of the original array. It's very simple to know it by check if we are at the start of on the left here. I speak on the left. Are we on the beginning of this block? The answer, as you see, is no here. We are not on the beginning or on the start of the current block. So we have to compute the start of the next, just next block here, which is, let's call it L1. Let's call it L1 here. The start of the next block, just next L. So this range will be now from L to L1 minus 1. Now we have the start of this block. Let's see what's the end of a block on the right side. On the right side we have R here. We have to check if R is the beginning of that block, if R is the end of this block. R is not the end of this block, as you see here. So we have to compute R1, which is the start of the current block. Of course, if we compute R1, we can know the end of the previous block, which is R1 minus 1. Now we can compute on the array B, array of block, all the blocks from L1 to R1 minus 1. You could have many blocks here, not just two like in the picture. You can have many blocks. You can, let's draw it here. We have L here. We compute L1. So the start of the next block, next of L here, the next, this is L. And we have many blocks here, and we have R here. We have R. We can compute, if R is not the end of this block, we compute R1, which is the end of the just previous block, the divided previously of R here, and we can compute all these if this all are blocks here. We can compute on the original on the array B, all the minimum of all these blocks from L1 to R minus 1. As you see in the picture here. So here SMRQ L R, as we will see in the beginning, we can use the sparse table to compute this minimum. By using this formula, of course, this is the left boundary on the sparse table, and this is the right boundary of the sparse table, of this range of the array of blocks. We can use the sparse table and compute this minimum on constant time. You may be asked why we divide by BS or log 2 of n to know the number of blocks. If of course L1 here is the index in the original array A. So to know which block correspond to that index, we divide by BS. What about the two others now? How to compute the minimum range query from L to L1 minus 1 and from R1 to R. Of course, we have to make it in constant time because we have to keep the constant time of a single query here of the sparse table. Does not make sense to make it, for example, in log n or n.